last talk in this session is by Xueyu, and the title of the talk is Sequence-Independent Lifting for the Set of Submodular Maximization Problems. Please go ahead, and the rest of us mute ourselves.
Yeah, hi. Can you hear me? Yes.
Yep.
Yep, cool. Thanks, John. A very interesting talk. And this is Xueyu from University of Pittsburgh, and I'm now working with Oleg Prokopiev and Boson. So today our work is about sequence independent lifting on the mixed integer nonlinear set. So we consider a mixed integer nonlinear set involving a single continuous variable W and n-dimensional binary variable X. So we have a constraint that involves a compute function, G. So in general, the convex Hall OP is a polyhedral because it's the union of finite extremes with same directions. Also, the optimization problem over P actually is hard in general, even if in some simple assumptions. We always refer to this set as the submodular maximization set because it has close relationship with the submodular function. If we define a set function f such that for any subset S, Fs equal to GAS, then if all the components in A are all non-negative or non-positive, then F will be a submodular function. So to define the submodular function, we always first to define the incremental value of I, rho IS, such that it's the incremental value of I when a component I is added to the set S. So submodular function is to say that it contains a dimension marginal return property. The incremental value of I decreases when as the input set in which I is added grows from T to S. Because the submodular function from the definition is very similar to the concave function, but it has close similar properties with the convex function. So actually it's a very interesting structure inside the submodular function from the theoretical part. From the application part, the dimension return properties can be applied in different applications. For example, it can be used as the concave utility function in the expected utility maximization problem. For example, the exponential function. It can also be used as a diversity reward. The concave function G can be the power function. And in some probabilistic coverage maximization problem, the object function is a product of probability. So the concave function G can be expressed as the exponential function by reformulate this problem. So also log function or some piecewise linear function can also be special case of the submodular functions. To deal with the submodular problem, Nemhoza and Wusi in their interior programming book, they propose the submodular inequalities to formulate P as the mixed 0-1 linear set. So you can see that for any subset S in N, they propose two classes of value inequalities for P. So this formulation actually can be applied to any submodular function. However, the LP realization of this formulation is quite weak. It can only solve small incidences. Furthermore, actually, we can only find two phase independent for convex Hall P, for empty set and for the entire set N. It defines the phase independent. For other subset S, for other non-trivial subset S, their corresponding submodular inequalities don't define the facet for the convex Hall P. So therefore, our first question is, can we get tighter value inequalities through lifting procedure based on the above facet defining inequalities? So this, so the first work is is done by Ahmad and Atmark in 2011. They did the lifting procedure to get the strong value inequalities. So our work revisit this lifting procedure and to get stronger result. So for the lifting, we first project the project P to a low dimensional mixed 0-1 set. So given a set S, we fixed the variables in the complement of S to 0. And then we can get the submodular inequality defines a facet for this low dimensional mixed 0-1 set. So the lifting process is to lift the star inequality to the value inequality of convex P. And to compute the coefficient of each lifting variables, we need to care about its lifting function as gamma 0. So in general, we would like to, in general, the lifting process is to lift the variable in a sequence, but the common idea is to consider the sequence independent lifting because it can save the computational sources. And the subactive and superactive functions are always considered as important properties to do the sequence independent lifting. So in general, some subactive function, if we can find a subactive function C, such that C is greater or equal than the lifting function gamma 0, then we can obtain our value inequalities by compute the coefficient of the lifting variable by using this subactive function C. In particular, if we can verify that lift function is subactive, then we can show the lifting is sequence independent, and then our lifting function is a facet defining for the convex hull. So it's stronger result. And in previous work, Ahmad and Atmark show that the continuous relaxation of the lift function by removing the integrality constraint, they can obtain a subactive approximation. So if G is a strictly concave, increasing and differentiable, then we can use KKT conditions to solve a convex problem and to get the explicit formula of this approximation. This idea is further applied by Ahmad and his PhD student Yu for the convex OP when the feasible region X involves a cardinality constraint. So our result is stronger. We show that we don't need any approximation because the lift function gamma 0 itself is subactive. So therefore the lifting is sequence independent, and we can obtain a class of facet defining for the convex OP. Furthermore, we only assume G is a concave function. So we don't need G is strictly increasing and differentiable. So we can study a more broader class of concave function. For example, the piecewise linear function we will discuss later. So this is our first result. We show the lifting function is subactive. So I will give a brief idea that why the lifting function gamma 0 is subactive. So we first sort the set S in a decreasing order with respect to the weight vector A. And we define the capital AK be the sum of the first K component with respect to the weight vector A. So in the left figure, you can see the figure of the lifting function. So first, the lifting function is a piecewise concave function, and it's concave on the interval AK to capital AK plus 1. So these are two basic observations. And to show the subactive, we need to verify this condition. And if gamma 0 equal to 0, also in here, the gamma 0 is the 0. So in the first piece, we want to, so therefore actually this definition is very similar to the concave function. Concave function is naturally the subactive function. So if Z is in the first piece from 0 to capital A1, then the lifting function gamma 0 is naturally concave in first piece. So therefore, we can show it's clear that it satisfies the subadditive condition. And if Z in the second piece from capital A1 to capital A2, then the curve we can verify that the curve of the lifting function at the second piece is identical to the subpiece of the first piece. That is a copy of the subpiece of the first piece. So therefore, to verify this subadditive condition, in the left figure, the green curve from capital A1 to Z1 plus Z2 is identical to the green dash curve. So therefore, we can reduce the subadditive condition to the right figure. We can verify that the incremental value in the red curve is larger than the incremental value in the green curve. So this is the subadditive condition we can verify. So similarly, we can verify this subadditive condition in the following pieces, because in the following concave pieces, the curve is just a copy of their previous copies. So this is the basic idea that we get the intuition that the lifting function gamma 0 is subadditive. Furthermore, we can develop a more generalized subadditive functions, which is piecewise concave function. We will discuss later that the lifting function of the flow cover set is a special case of this subadditive function. So on the other hand, we can also lift the variables from 1 to 0. So we can give a set S. We first fix the variables in S to 1. Then we get a low dimensional mixed 0-1 set and get a facet depending inequalities for this low dimensional mixed 0-1 set. And to perform lifting, we calculate the lifting function as at a 0. So again, if this at a 0 is subadditive, so in general, the common idea is to do the approximation. But if we can verify this lifting function is subadditive, then we can obtain a class of facet depending for the convex OP. So this is our result. So similar to the uplifting result, we show the lifting function is subadditive, and we only need the assumption of G is concave. So this is the result we strengthen Emmert and Antomok's previous result. So in our computation, in our preliminary experimental result, we consider the expected utility maximization problem. We compare the approximate lifting inequalities from previous work and our exact facet defining lifting inequalities. So you can see in the table that by using the exact lifting inequalities, the problem can be solved faster. And the normal cost can be substantially decreased, because you can see, especially for large instances, we only need maybe 800 cutting planes to solve the problem. And the problem can be solved at a root node by using the exact lifting inequalities. So it means that, so you can remind the figure that the difference, you can remind this figure that the difference between this approximation lifting inequalities and the exact lifting inequalities is very small. The marginal between these two inequalities is very small. However, through the computational result, you can see that this small difference can make big difference, because it might require 10,000 cutting planes compared to several hundred cutting planes with such small differences. So it implies the cut inequality for the mixed integer nonlinear set is very important. So far our basic results show that the lifting functions are subactive, and the uplifting and downlifting are sequence independent for this mixed integer nonlinear set. Actually, this is not a very common property because the subactive function itself is sequence. The lifting function itself is subactive. It's not a very common property, even in the mixed integer linear set. So they have two classes of a mixed integer linear set. First is for mixed 0-1 knapsack set. It involves a single continuous variable pi and binary variable x with knapsack constraint and lower bound constraint. So Matroid and Xueyu show that the uplifting and downlifting for the mixed 0-1 knapsack are sequence independent. And for the other example is for the single node flow set. So the lifting function of the flow cover inequality for the single node flow set is superactive, is shown in by Gu in 1999. So therefore, our question is, can we build connections between the submodular maximization set and this classical mixed integer non-linear set, because they all have such special property, such special sequence independent lifting property? And the answer is yes. So for the mixed 0-1 knapsack set, we can reformulate K. We first move the continuous variable pi to the right-hand side and merge these two, merge the lower bound constraint and knapsack constraint. We let W equal to minus pi and define a concave function G as minimize B minus Z 0. So therefore, actually, the mixed 0-1 knapsack will reduce to the form of the submodular maximization set. Especially, the construct concave function G actually is piecewise linear function. It's not strictly monotone or differentiable. And for the single node flow set, we can define a convex function GZ as a piecewise function. It's a maximized 0 Z minus a number. So in the figure, you can see, actually, we can see that actually the lifting function of the flow cover set inequality phi Z is a piecewise convex function. And if we do some reformulation, we can reduce this lifting function to the form of our lifting function gamma 0. The only difference is that the function G is convex instead of concave. So actually, we can give a simple proof that this lifting function is a superactive function. So therefore, we can build the connections with the mixed 0-1 knapsack set and the flow set, the single node flow set. Also, they have some well-known developed result for this classical mixed integer linear set. So for example, the Atmark studied the facet for the mixed integer knapsack by considering the general integer of x. And also the dimension of the continuous variables becomes m. And when the other example is when the feasible region X is a partition Matroid, that is, X involves a multi-disjoint catenatic constraint, Zheng and Richard show that the lift function for the single node flow set is also superactive. So therefore, our question is, can we develop similar result to Atmark for the submodular function, to the submodular maximization set when X is a general integer? Also, can we develop similar result to Zheng and Richard for the submodular maximization set when the field bridging X is a partition matroid? And the answer is yes for this lifting. If we consider a partition matroid, actually our constraint is multidimensional. To do the lifting, we first project P to a low dimensional mixed 0-1 set, and then we consider the sub-infinity as a sig infinity, and we consider the lifting function as gamma Zu. So we know that in this lifting, we need to consider multidimensional lifting function because we need to care about the partition matroid constraint. So the multidimensional lifting has two challenges. First is difficult to calculate the lifting function gamma. So this is difficult. Second is difficult to verify the sequence independent lifting conditions. And our result, like we said, we show that this multidimensional lifting is also independent, is sequence independent. So therefore we can obtain a sequence independent, a class of facet defining for the convex of P when X is a partition matroid. So this is also the cardinality constraint is also a special case of partition matroid. We won't discuss the details of the proof, but we need to point out some difficulties in the proof. So first is we can't show the lifting function gamma Zu is subactive on the whole space. In general, to prove the theorem, we need to show the stronger conditions. And in here, we show the sufficient and necessary conditions for the sequence independent lifting. And in general, this multidimensional sequence independent lifting framework proposed by Zheng and Richard cannot be applied for this mixed integer nonlinear set. So therefore, our next question is, can we propose a more general lifting framework in the future? So to conclude our work, we first strengthen the previous work by Ahmad and Edmond for the submodular maximization set. Also, we reunify and we build the connections between the submodular maximization set, which is a mixed in 0-1 nonlinear set, and between this connection with the mixed 0-1 knapsack set and the single node flow set, which are mixed integer linear set. And finally, we develop the multidimensional sequence independent lifting for the mixed integer nonlinear set. And we develop a class of facet defining inequalities for the convex Hall when the phase region X is a partition matroid. So this is my talk. Thank you for the listening. So any questions?
Are there any questions? Please unmute yourselves and ask. I don't think we've had any congestion problems otherwise. It's a little bit on the early side. Okay, well, thank you very much. That was a very nice talk.